Yeah, awesome. Full room, that's nice. Welcome, Ide. Welcome to the JFall 2019, to our talk, Deepfakes 2.0, how neural networks will change our world. And before we start, we want to introduce ourselves. So, Thomas.
Yeah, so my name is Thomas Endres. I studied computer sciences. And after my studies, I joined TNG Technology Consulting. And there we are working on innovative prototypes of all kinds. So last year we had a talk about how we can see the world through the eyes of an artist. And this year we are talking about deepfakes.
Yeah, deepfakes. So my name is Martin Förtsch. I've studied computer sciences as well. And it's not our bread and butter job that we are working on innovative projects, but we have 10% of our working time where we are allowed to work on such things we will show you today. Normally we work on projects which are based on artificial intelligence, or we do agile software development, DevOps and clouds, and so on. Okay, why is there this guy, Jonas Meyer? Yeah, he was back in the days an intern who worked very hard on the deepfakes we want to show you today. And we want to honor that, so Jonas is here as well. Thomas, can we start right now?
Yeah, we can start. And Martin, before we start, I want to show you something because I saw something and it is...
Oh, you saw something?
Okay. Yeah, it was on the internet and you won't believe it. You know this guy?
This is Barack Obama.
Look what he said.
President Trump is a total and complete dipshit.
Hey, come on. No. He never said that. No.
It was from YouTube, so it must be true.
Can you show me?
Yeah.
President Trump is a total and complete dipshit.
No, come on. He never said that. You saw it on the YouTube University. No. Come on. Have you ever heard of deepfakes?
What?
Deepfakes. This is why we're actually here.
No.
Okay. You should always see the whole video and not only a fragment of that, okay? Let's have a look.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time.
Yeah, this is a dangerous time. So we know that the topic about deepfakes is a very controversial topic, and there are some professors working on such things as well, like Carl Bergstrom. He's generating fake faces based on artificial intelligence from the University of Washington. And he said, when a new technology like this comes along, the most dangerous period is when the technology is out there, but the public isn't aware of it. That's when it can be used most effectively. So this is the reason why we give a talk today about deepfakes. At first, we want to differentiate between all those different things which are called deepfake, but which are in fact not deepfakes. Then we want to introduce you to one of the very first implementations of deepfakes. Then we want to show you our implementation, which is real-time, working in real time. Then we want to speak about fields of application and the conclusion. So let's go back to the Obama video we just saw. So what happened here? So we have some audio waveform which sounds like the voice of Obama, so it was mimicked. Nowadays you can use artificial neural networks to generate such voices, which sound very natural. But here in this case, we are using the audio waveform to receive mouth tracking data. So a recurrent neural network takes the audio waveform, and we have mouth positions. And with the help of this position data, we can have a look into the whole video sequence. We can check, okay, this lip position is very good for this audio waveform, for this phoneme, and then we just make resynthesis. So we take the mouth from a special timecode and we put it somewhere else. And afterwards, we have a final video and it looks like that Obama is saying things he would never say, at least not in the public address. So in this case, only the mouth gets replaced based on retiming of the timecode of this fragment. And that's it. So it's not really, it's not a deepfake. It's just not a deepfake in this case. Next example.
So let's have a look at some other example. This is a face swap, which can be done by classical apps like Masquerade or others. And it basically just takes the face of one person, puts it on another person, and that's about it. So it's a very simple technique, and the illusion breaks down pretty quickly if someone puts out his tongue or holds a hand in front of his face, and so on and so on. So it is too simple. It just uses some basic machine learning techniques. It is not a deepfake at all. So this is also not approved.
Right.
So we looked a bit further and we came across an example from the TU Munich. And this is real-time facial reenactment. So what this does is it takes the mimics of a source actor and projects them onto a target actor. Whereas the target actor is basically just a closed video loop, which is repeating again and again and again. And there we are taking a parametric model of the face. We are applying this both to the source actor as well as the target actor. And then we are transforming the model of the target actor to fit the model of the source actor. And based on this representation, we can then redraw the scene so that the target actor looks like he would have said exactly what the source actor is currently doing. But as this is not using AI at all, it is basically just a classical optimization, which we are doing here. So this is also not a deepfake. It's not approved.
Not approved as a deepfake. So for all those things, yeah, there are scientific papers existing. You just can read them and then do whatever you want with this information. So the idea was, okay, we need some scientific paper about deepfakes, the real ones. So we searched a long time for that, and there was a problem. We didn't find anything. The only thing we found was a thread in this forum. Yeah, there was a guy, I think his name was Deepfake or something like that. And so he was creating videos, and I don't know.
Yeah, he was basically trying to get his favorite actors into different movie genres or something like that.
Yeah.
So,
so for science reason, we just researched videos. We watched many videos. And actually, we found one we can show you today at this conference without getting kicked out. So this is from the movie A Batman, right? And on the left side, you can see Amy Anderson, yeah, and
Adams.
Excuse me, Amy Adams, and on the right side, it's Amy Adams as well, but with the face features of Nicolas Cage. And let's scale that. Let's zoom in, and you can see. To be honest, it's really good, right? It's really hard to identify that it's a deepfake. Yes, you can see it because you know Nicolas Cage, but yeah, it's really amazing. This thing, what you can see here, is created by a deep neural network, which was trained on Amy Adams and Nicolas Cage face. And this gets generated, and this is a real deepfake. It's approved as a deepfake. Okay, and now we want to introduce you how you can create them. What is the workflow behind that to understand the whole thing? So we want to start with a video of Shia LaBeouf. So please don't be scared right now because we want to hear a motivational speech, okay? Yeah, Shia LaBeouf is an actor who played in Transformers, I think, and let's go on.
Don't let your dreams be dreams. Yesterday, you said tomorrow. So just do it! Make your dreams come true!
Yeah, Shia LaBeouf. So maybe you recognized something right now. Can you see something? Can you see it? It's not Shia LaBeouf anymore, to be honest. It's more Martin LaBeouf. And what we did here was generating a deepfake using the Deepfakes Lab repository, which is hosted on GitHub. Several gigabytes of data. You can just download it and you can create your own one. So on the one hand, you see the original video of Shia LaBeouf and then the deepfaked video. To generate something like that, what do you need?
Yeah, of course, at first you need input material, and this is a video. So we took Martin and he is fooling around in this video a little bit. We actually need this fooling around. We need a sad Martin, we need a happy Martin, we need a smiling Martin.
A wide variety of emotions.
Yeah. So you need something that you can replace the original emotions with, and therefore it has to be, quite interesting.
No. Yeah.
And then, of course, you need the input material from the original video.
Yeah.
So what do we do with this? So first of all, we have to do some preparation, so dataset preparation. And this has to be done both for the source video as well as for the destination video. And what we do here is we first take the video frames from the video. We then do a simple face recognition. We extract the face from this frame, and then we align it so that it is central within the image. And we do this, of course, for both videos. Here is a small, here it is detailed in some more detail here. And as you can see, we are detecting face landmarks. So these are points in the face. We have 72 landmarks for the FaceNet neural network, which we are using here. And this is creating this landmark pattern. This can then be used to align the face so that it is aligned centrally within an image. And this can then be used for the neural network.
Yeah.
So let's have a look at how this looks like. Here you can see Shia LaBeouf again, and for each frame we found the face landmarks and also the bounding box, which can then be used later on.
So this video is not a live video. We just took those processed frames and put them together in a video sequence because FaceNode is not that fast. It's a bit...
let's have a look at it.
Yeah,
we have a live demo here, and you will see in a second.
Hopefully, it's a live demo.
So here you can see Martin, and you can see the different landmarks and also the bounding boxes which are created here. So as you can see, it's not live, and it's roughly 2 to 3 frames per second. So this cannot be done in real time, actually. But it is one of the best algorithms for detecting face landmarks at the moment. And it is also used for things like Apple Hello.
Okay.
Good. So here you can see the different aligned faces. So the nose is always some kind of central within these images. They look straight at you. The faces look straight at you. And this can now be used for our neural network, which is an so-called autoencoder.
Right. Yeah, we have to train our autoencoder, and for this we are using this data. And what is actually an autoencoder? It consists of 2 parts. On the one hand, we have the encoder, and you can just put in some input image, for example, a face. And this face gets reduced to its main features within the latent space representation. So such features could be the eyes. Are they open? Are they closed? What about the mouth? Is it open? Is it closed? And so on. What is the angle of the face, the rotation, and so on. And the idea is that you can reconstruct the image based on these features inside the decoder. And we want to have a deeper look onto this right now.
Yeah. So here you can see what happens with the images. So we take the image from Shia LaBeouf, put it into the encoder. There it is compressed to its main features, as Martin already said. And then it goes to the destination decoder, where it is reconstructed. And ideally, in an ideal world, we would get the same image out again. Of course, in the real world, we have some losses, but it looks pretty much the same. And what we have here is one encoder, but two decoders actually. So we put in both the images for Martin and Shia LaBeouf into the encoder, but the decoder is different for the two faces. And what we can do now is we fool around a little bit. So we take the image of Shia LaBeouf, put it in the encoder, but put it in the wrong decoder afterwards. So we get the same mimic as Shia LaBeouf, but with the face of Martin, because it reconstructs the features that it sees in the encoder with the decoder of Martin. And then we get a Martin LaBeouf.
Right.
So in this picture, you can see how training works in the original implementation. So here we have the input for the destination. So this is the target actor, so to say. This is then the reconstructed decoder output. So as you can see, it looks basically the same. It is
Which
not
actually means that it's trained well enough already.
exactly. And then we have the same for the source actor, which is Donald Trump in this case. And in the final column, we see how it works when we take the mimics or the facial expression of Donald Trump and put it onto Nicolas Cage. And this is the result then.
Yeah.
Yeah. Okay. So now how do we train these neural networks? It's pretty simple because we can just put in the different faces, see the results, and then we can compare these results pixel-wise. So we can just say, okay, what's the difference between these two images? And if it's pretty much the same, then the loss is small. If it's not the same, then the loss gets bigger and bigger. And we do this for both of the encoders, of the autoencoders. And then we can train this neural network.
Let's continue. So what we can see here is the neural network is starting to train. And in the middle column, you can see that actually there is not much going on. It just learns how the face of Shia LaBeouf in the upper middle looks like. And the more iterations we have while training, something happens. It's starting to rotate, so the neural network just learns that a face can have some kind of rotation. And if you continue this training, you will also see that features like open or closed eyes and open mouth and some more complex emotions get learned by the neural network in this case. Yeah.
The longer you train, the more complex it will get.
Right.
And you will have some real deepfakes then.
Yeah. So let's have a nearer look to the workflow again. So we take a video frame, here in this case, the original Shia LaBeouf. Then FaceNet is identifying, aligning, extracting the face. Then we put this information into an autoencoder. This puts out two information: the suggested face with a fitting mimic emotion, and additionally a mask which can be used to blend the suggested face into the final video frame, which is then a deepfake. That's it, how it works. And now we want to talk about the implementation we did for Deepfakes 2.0. So we want to talk about the motivation. Yeah, it's not our bread and butter job, as we already told you. So there is no customer saying, hey, I want deepfakes in real time. But we wanted to check what's possible today. So we had the idea, what if we can make deepfakes work with any face? So the idea was not to have only those two faces we have to train all the time. The idea was stand in front of a camera and ideally your whole head gets replaced by another head. Yeah, this should be done in ridiculous speed. Yeah, so real time, as we already told you, and clean code. So if you are strong enough, have a look to Deep Face Lab GitHub repository and have a look to the code, and you will understand why. Okay, so now we want to have a look onto this workflow again, and we extract the parts where we made some optimizations, yeah? And here we start with the face recognition and face extraction. We told you that we used FaceNet on that at first in the original implementation, but we optimized here something, and we want to tell you what.
Yes. So basically, FaceNet is not, we cannot use FaceNet here. It is just too slow. So we need to replace it with something which is way faster. And the best way to do this is actually for us to use OpenCV, because OpenCV has an experimental new feature called DNN, so Deep Neural Networks. And with this, we can just load neural network definitions as protobuf files or something like that. And we can then do an inference using OpenCV. It is purely done on the CPU, but this is fine for us. And there are even examples on the OpenCV homepage which you can download and with which you can do things like face detection.
There are a lot of developers here. We should show some code. It's a Java conference.
Yes,
maybe some Python code would be cool.
So, yeah. As you can see, Python code is way cleaner than Java code. No,
that was thin ice.
I hope we do not get thrown out now. So what we can do here is we can read the neural network from a model file and then get the weights in using a second file. And with this, we already have a neural network then. And then we can put in the input image into this neural network, and we'll have prediction, which we can then read. And these are the face candidates. And then we already have our face candidates. So this is all the code you need for face detection using a pre-trained neural network and OpenCV. So it's pretty simple.
Demos already didn't happen. So let's do a live demo. And yeah, I hope it works. Yeah. Awesome.
So here you can see Martin, and you can see that it's pretty fast on the one hand, and it is pretty robust on the other hand. So even if Martin is putting his hand, if he is standing sideways, if I get into the picture, you can see two faces. So
works like a charm, isn't it?
Works like a charm, and it was quite enough for our taste.
Yeah.
So
now we have the region where we have to do some further processing, right? That was the idea why we want to identify a face here. So, I like this picture. Thomas looks a bit sick. What we do right now, what we want to do right now is we want to do face segmentation. As we already told you, we want to replace the whole head. Yeah. So we do a segmentation, and how did we implement that?
This is actually a bit crazy. So actually what you see in this animation is exactly what happens. We take a fast neural network, a so-called mobile net, I think it's V2 in this case, which is basically just a classification network. So you can say this is a car, this is a cat, or something like that. Then we just cut away some of the layers, some of the later layers, and we take a second neural network, just put it where the original layers were, and we take a UNet, put it there. A UNet is a second kind of neural network which can be used for segmentation. And then we use a pre-trained mobile net, and we use an untrained UNet, and we train this with pictures of celebrities. And using this approach, we can then segment our images as we get them in a very fast way.
Yeah.
And there's also a fun fact, because how did we actually train this? There was one guy who was segmenting faces by hand. So he took pictures of 30,000 celebrities, said, okay, this is the face, this is the hair,
these
and
are
so
the
on,
ears,
and so on and so on. And we could just use this data to train our network to segment only the face.
Yeah. The reason
So
for
thank you very much for
why
that.
celebrities, because there are existing many face photos from different angles, yeah, and yeah.
Actually, celebrities like to look directly into the camera.
But
That's
not if it's a paparazzi.
maybe.
Or maybe? I don't know. Okay, so here again we have a live demo for the face segmentation. So let's see how it works.
So Martin is looking a bit sick,
I look like the guy from the Blue Man Group, but yeah.
and as you can see, it's done in real time.
Maybe-
It's not perfect, but it works quite well. And the reason why it's not perfect is also because the lighting conditions in this room are not perfect as well. But we will get to this when we get to the main demo.
Yeah.
And if Martin turns his head, you like this,
Ach so, okay.
rotate your head.
Mhm.
You can see that parts of his it's not clear where his face really ends, and this is due to the fact that I just told you celebrities look directly into the camera and not from a side angle.
Okay. Let's stop the demo. Let's
Okay.
continue. So now we have the face segmentation information. And now let's talk about the part of mask and mask blending. Yeah. So, okay, when the face is segmented, we just put another head on this face, segmented face. So let's look at this example. What if Thomas' head is placed on my head? There is a huge problem. Sometimes we have these strange overlays. So the original head is still in the video frame and the fake head is placed over that. And this is not a really good deepfake experience. So we have to get rid of my head. In this case, this could be an idea. And for that, you can use OpenCV image in painting. Image in painting is normally used for fixing broken photographs, yeah, which are very old, where scratches are on it and so on. And you normally use that. And the code for that is really, really simple. Let's have a look here. It's just calling the method in Paint with the input image, the mask. We have the mask. It's the face segmentation. Yeah, remember?
Normally, if you take the pictures, you would just mask all the scratches that you have in an image. But now we have a huge scratch.
Right. Yeah. Thank you. And then you just can choose between two methods. In this example, we are using InPaint Telea. There are different implementations existing. This is a really, really simple one. And we prepared a demo for that as well, so that you have an idea how it looks like. So ideally, my head is now gone.
Yeah. It looks way better now.
Yeah. So, and this is how image in painting works. I can't see that, so Thomas.
So your head is really replaced, and you can see a bit how this works because it's based on a so-called fast marching algorithm. So from outside to inside, pixels are a flow into this region of the mask, and this is how it works. And whenever Martin is moving his head close to the bright surface, then you can see that it is in some places not really ideal.
But maybe it's not ideal, but it's good enough for our deepfakes here in this case. And that's
in this case, you draw another head over Martin, so you won't really see that this is not perfect.
So now let's talk about the autoencoder. So we learned in the original implementation that you have two faces. Yeah. So
two faces were basically not enough because you need to train the autoencoder for different situations. So you have all kinds of different people standing in front of the camera. So you have to really train with more than just two heads, because you want maybe people with glasses or long hair, all things that we didn't do even in our implementation. Therefore, we used several decoders now, but still the same encoder as in the original implementation. And at the moment, we are talking about 7 different decoders that we are using. And they are trained with Donald Trump, with Neil deGrasse Tyson, and all kinds of people who look not the same at all. Yeah, and there's a basic problem with that because we get things like that if we just use the original implementation or Picasso.
What happens very often is that we have a second mouth here on the skin, and was a very strange nose.
The forehead eye is very common, actually.
Yeah, the forehead eye. Yeah, and the best picture actually was this one, the Barack Obama alien. Yeah. Okay, so we have to solve that. The autoencoder. Sorry.
Yeah.
Right. We have to solve that, and now we have to discuss generative adversarial networks.
And they are a bit like.
Fight!
Yeah. Generative adversarial network. It's a fight between a generator and a discriminator. And we want to do an offline roleplay game now, so that we want to describe how it works and how we can improve our quality of data which gets put out. So, Thomas, you will be...
I will be the discriminator this time.
Like in the regular shop, you are the discriminator and I'm the generator, right?
I'm always judging you, so that's always better than just generating.
Okay, so we start with round 1, hopefully.
Round 1.
Perfect.
Fight!
Okay, so I'm the generator and I have to generate something, and the discriminator has to decide if it's real or if it's fake.
Yeah, but to decide, I have to be blind now,
right?
While you are creating the image. And keep in mind, we are still untrained.
Yeah.
So, like in our normal lives.
I'm a newly initialized neural network. I don't know what to do, where to do, and how to start. I only have the task, please draw something, and he will decide if it's a fake face or a real face, okay?
And at the same time, I am a completely untrained discriminator, so I don't know anything about anything.
Yeah. Okay. So, Thomas, let's start. I'm uninitialized, and I don't know what to do, so... I'm just starting with some kind of noise, maybe. That's cool. Discriminator.
Yes.
I'm finished.
You're finished.
Okay. Please make a decision. What is the fake face and what is the real face?
What is a face, by the way?
You don't know, yeah, but you will learn.
Okay. Learning by doing. Okay. So I don't know. I'm totally unaware of anything, so I'll just have to guess right now.
So normally Thomas would start to guess for the noise, for the actually the real face, without any idea what he's actually doing. But there is a specific point in time where he definitely learns, okay, if there is just noise, it's wrong, it's fake, yeah. So he will learn.
Thanks for that. I'll take the right one. I learned.
Okay, of course, that's the real face, yeah. So now let's go to
round 2.
Okay, I learned as the generator, just generating noise is not a good idea, because he already learned what eyes are, or a mouth or something like this is. That is. So I tried to draw something which is really hard for him to guess, I think so. Okay. Sorry, it's the best I can do. Discriminator?
Yes.
Sorry. Yeah, this one. Yeah, please.
Didn't see anything. Okay.
Yeah, which one is fake and which one is real?
So, Martin, you are really getting good at this. From previous iterations, I learned that a face consists of eyes, a nose, a mouth, maybe some teeth. Yeah, okay. And, So both of them are quite good from my current knowledge. And I would say hair is missing. Yeah, hair is missing. So I'll take the left one.
Yes, you're right.
Yes.
Okay. Oh my god. Okay. Now the last round. I do my best, but to be honest, I can't do that.
Round 3.
We take a real
Fight!
generated fake face in this case. So Thomas, what would you say? It's really hard right now.
It's really hard. So I give up. Actually, I think they are both the same.
We want to have a look to the schematic view to the generative adversarial network right now. And Thomas, yeah.
Yeah. So this is exactly how a GAN network really works. So we have the generator which is creating generated faces. On the other hand, we have a discriminator. The discriminator is fed both with the generated faces, but he is also fed with real faces from just photos, actually. And then the discriminator has to decide, is this a deep fake, or is this a generated content, or is it a real content? And based on this, it is learning. So we take the loss and we train both the discriminator with that as well as the generator. So both the generator and the discriminator get better over time.
Right. So now we want to show you the full live demo. And for this, we need brighter light. So yeah, the technician is just running. He said he needs 5 seconds. Wow, that was really quick.
5 seconds.
Okay. Hopefully it works well enough. So let's have a look to the live demo. And it's the inference just working on this laptop here.
How does it look?
And yeah, it's a bit better, but it's not perfect right now. And yeah, you can actually see Thomas Tyson here. And all the mimics Thomas is doing, they are mirrored by Tyson in this case. So please excuse, because of the light conditions, it's not the best quality here. Anyway, also with good light conditions, you would identify this as a deepfake, of course. And the reason for that is that this neural network is just trained for 3 days on a machine with 2 NVIDIA 1080 Ti graphic cards. Yeah? So please keep that in mind. And you can also identify this as a deepfake because of the missing details in the skin, for example. Yeah. And yeah, this is the most awesome software I've ever seen. Yeah, right. Okay, so now please think for yourself what will happen if you take a lot of money, you improve the software, and you will train for several months on powerful machines. Then you can maybe get an idea what will happen in the future. And yeah, these are real-time deepfakes. We are currently training on a very powerful machine, and we hope that we can improve the results here in this case. So we checked everything.
Yeah,
awesome.
I think we're through.
We are through. Perfect. So, yeah. What are the fields of application, you may ask? Yeah. Let's have a look. Movie industry, for example. Can you guess which is the CGI version and which one is the deepfake version? You probably have to guess. You don't know which one is the real one because they are really good. And I can tell you that the upper one is the CGI version and the bottom one the deepfake. What is the difference? The cost of it. The upper one costs hundreds of thousands of US, and the bottom one only, let's say, a few days training on a powerful machine. Yeah? Yeah, awesome. But, of course, it will also get used for generating fake news. That's clear.
But we said it before when we discussed the GAN network or the generative adversarial network. It cannot just be used for creating fake news, so this is the generator part, but it could also be used for really detecting fake news or deep fakes.
Yeah.
So we can just train it with real data for a long time, and then we can use it as a pre-filter for YouTube videos or something like that, so that you cannot upload deepfake videos.
Yeah.
This is not feasible at the moment because the training is just too specific right now, but in the future this could really be a field of application for this kind of deepfake.
Yeah. So we worked on deepfakes in real time to make the public aware, like Carl Bergstrom said, that there is something going on. So it's not only a deepfakes based on post-processing videos. So maybe in the future we can not trust video live streams. So keep that in mind. And yeah.
For us, it was more or less a research project. So we wanted to show people what is possible with today's technology, what you can do. We are currently still improving on that. So what you saw right now was highly dependent on things like current lighting conditions. But it's also dependent on my glasses. So I took my glasses off because we did not train with people who had glasses on in the first place. And it also does not work for people with long hair at the moment. Same reason we did not have a person with long hair in our training data, actually. And there are still some other caveats which are being worked on for now. But we did this with a very small budget. We had worked on it for 5-6 months or something like that, or so person months. And if you take $1 million budget and try to do the same, you will end up with near photorealistic deepfakes in real time.
Right. So what is the state of the art when it comes to deepfakes or style transfer living portraits?
Yeah, our last demo from last year was actually called Style Transfer. And there you could see the world through the eyes of an artist. So it transformed reality into a work of art based on a specific style from a specific painter. And now we can actually combine two techniques from the field of AI. So we can combine style transfer with deepfakes, and then we can just create a living portrait. We can take a famous painting and we can create a deepfake from it, which comes alive based on the mimics of someone else.
Yeah, if you are interested about the style transfer talk, you can have a look to this QR code, and we invite you to have a look on this. Okay, so now we fortunately have some time because we are quite sure that there are questions in the audience. So our talk is actually finished here, and we invite you to ask questions if you like. Are there questions in the audience? Please. The question was if our model doesn't use face landmarks.
Yeah.
Yes, we don't use face landmarks.
So the question was if this would be an improvement. Actually, for us, it would not be an improvement at the moment because face landmarks just use the contour of your face. And when it comes to the deepfakes, the first implementation of deepfakes, only the part in there was replaced. But we also want to replace things like hair and things like that. So the segmentation is actually working better than the face landmark detection in our case. And we can still improve on what we did if we just have more training data for the segmentation model. So if we would pay someone to segment faces that are rotated like this towards the audience, then it would get better. Yeah.
There are other questions. Yeah, please. The question is if the performance stays the same
with more training
with
data.
More or less training data. So
it does not really change based on the training data, actually. So the encoder network is still the same, and So you still have the same amount of data which is loaded into the GPU. So what we do is it just generalizes the features of the face in a more abstract way if we put in more faces. So the weights are more useful for detecting different faces. What changes the performance is actually the amount of people really standing in front of the camera. So there we have to do it in batches, and this is done, has to be done multiple times right now. But actually, what the biggest performance impact is for our neural network at the moment is the CPU limitation, because OpenCV face detection is working with the CPU, and we trained it on a very, so we executed deepfakes on a very powerful machine a few days ago, and it was working worse than in our laptop because it had multiple cores, so 28 cores or something like that. And but each core was just idling except for one. And this one was doing all the work, was doing all the face detection. And therefore, we are currently improving on doing this on the GPU as well.
Another question, please. Yeah. The question was, is there any reason why the eyebrows, the upper part of the face, that they weren't recognized by FaceNet and maybe not used? I think the main reason for this is that in the original implementation of those deepfakes, not the whole head is replaced, it's just the main part of the face. And I'm not sure if can you, do you want to start the demo right now, or?
Yeah, it started.
No, I think the question was because of the FaceNet stuff,
yeah.
right?
Yeah, okay.
Right.
FaceNet, sorry.
Yeah.
I did get this wrong.
Yeah.
I'll start the FaceNet demo. Here we go. I think we...
Here it is. There, you can see. In this case, the upper parts are used. So till the eyebrows.
Yep. And the FaceNet implementation is not trained to detect the forehead, actually. And this has a reason, because hair is varying between people a lot. So people have hair which is going down there, a bob or something like that. And then we have people who have no hair at all. So this is, whereas the lower part of the face is pretty standard for all people, the upper part of the head differs a lot.
Okay. So one question, and then time is running out. So do we have another question? If not, thank you for being here, and we hope you enjoyed the talk about real-time deepfakes. If you have some questions left, just come over here, and we also have some business cards just in case. So see you and thank you.